Okay, so what we're going to do is not really deep or difficult. It's just about notation. This here is sigma. It's capital Greek letter for S, and S stands for sum. And we're gonna add expressions that look like this. We're gonna square a number and subtract the number from the square, and we're gonna add those. The starting value is 4, and then 5, and then 6, and this is the last value here. So basically this is just a translation. So this thing equals to, our first value is 4, so we have 4 squared minus 4. Then the second value, we roll up to 5, 5 squared minus 5. And then we roll up to the next number. And we do this all the way until we reach the number that's indicated on the top of sigma. And now there is nothing new, we just add this short little sum. 52, and we get 104. Okay. One more comment, when we don't see a sigma but rather a capital Pi, that's for product. But the idea is the same. You have a variable that indicates what expression we're gonna multiply in this case, and then the starting and the ending values are indicated. So here we're gonna have a nice little product. Namely, we start with j equals 2, so 2 over 3 times, and then we roll up. J is now 3, so we have 3 over 4, and then we roll up. J is now 4, so we're gonna have 4 over 5. Now j is gonna be 5 over 6, j is 6, and finally j equals 7 is our last one. And just before we start multiplying, just notice that there is lots of cancellations here. So basically this is 2 over 8 or 1/4. So this is just notation. This is our next example. The expression is fairly simple, 3 times k, and the first value of k is 2, the last value of k is 50. We will solve this problem too. Let's see, 3 times 2 plus 3 times 3 is 4, all the way till k is 50. That's the last one. 3 times 50. So then we might notice that we could perhaps factor out 3. And for the sum inside the parentheses, we have a formula for that. This one. Right? So if we add the numbers from 1 through n, that sum has a shorter form, n times n plus 1 over 2. Except in our case, we don't start at 1. But there is an easy fix for that. So we're going to say 3 times 1 plus 2 plus 3 plus 4 is 50. And then we're going to quietly undo the damage that was done. And so this we can compute now using our formula. So we have 3 times, n is 50, 50 times 51 divided by 2, which is 3. But again, the most important point is the translation from this compact summation notation to our usual better known notation. You may notice that the letter I is used in this last example. In my opinion, the letter I is just overused. You will see that this letter has a special role among complex numbers, among vectors. So I will avoid using the letter I in such expressions, but I wanted to show you at least one example because it's standard, so you're going to see a lot in the future, but not from me. In case of this particular problem, we're just going to translate it. We're not going to solve it just yet, but we will be coming back to this problem later. For the translation, the first value of I should be 5, and then 6, and then 7, and then all the way to 200. Obviously, this sum is a little bit longer than the previous ones. We might feel motivated to use the summation notation. We can just use our good old notation with the ... which is what we're going to do. When I is 5, we have 5 squared minus 2 times 5 plus 1. And then we roll up to 6. When I is 6, we have 6 squared minus 2 times 6 plus 1. then we go I is now 7, and now the reader kind of got the hang of it, and so we're gonna go all the way until 200. This expression is the same as this longer one.